So I don't know if you covered op-amps earlier in physics module. So I'm just going to do a introduction on that, and then later we're going to look at some applications of it. So op-amps are basically implemented using transistors and other circuit elements, but as we've not as we've done before, we're not going to cover the details of how op-amps are implemented. We'll mostly be studying the characteristics of op-amp, just like we've described before, this approach of behavioral description. So we're not going to see how we implement operational amplifiers using transistors. We're basically going to see how the op-amp actually operates, and then based on this description of its characteristics, we can work out circuits. And you know, op-amps are sold as chips, so it's used a lot in the field of sensing, in the field of interfacing, and as we go along, we will have a very good indication of what we can do with op-amps. Basically, op-amps is operational amplifiers, like the name itself is saying. Amplifier means you can use it to amplify signal. For example, from a sensor, if you're getting a quite low voltage, for example, if you are dealing with thermocouples, you would typically get very low voltages from thermocouples, so you can amplify this signal to a more reasonable range for your process, and then based on that, you can do more processing down the line. Okay, now like we've done for diodes, we've considered first the ideal diode, and then we came to real diodes that allow us to have a good understanding of diodes. So we're going to do a similar thing with op-amp. We'll consider the first thing an ideal op-amp. So what you see in front of you here is the symbols of an op-amp. So let's look at all the different pins that we have on it. So first is plus Vs and minus Vs, not always shown on in circuits with op-amps, but basically an op-amp is an active device. It needs to have voltage supplies connected to it. It's not like a passive device like you have capacitors, inductors, or resistors, or diodes. They don't have dedicated voltage supply attached to them as a circuit element. But op-amps would need a positive Vs and minus Vs, means your output signal, which you find here, Vout, can be maximum is plus Vs and minimum is minus Vs. You cannot go beyond this, because Vout is basically deriving the voltage from these two supplies. So this is your supplies, like I say, not always shown. So typically you just have a triangle and then two inputs and one output. So not always we have these supply lines, but we have to understand that they are always there. Okay. Now as inputs, we have two inputs, as you can see on the symbol. One is plus and one is minus. So this one, which we call plus here, V plus, is called a non-inverting input. Non-inverting in the sense it's not inverting the polarity of your input, and this one is an inverting input. This is the minus. So you have two inputs always, and then you have one output. Okay, so I'm going to send you the notes. Of course, you can have more information from your notes about all everything we're going to discuss here in more details. So, like I've said, you have two inputs and one output. Now, important for us is to understand what's the relationship between the V plus, V minus, and your V out. I'll see later. Your V out is very simply related to your input by a gain. So you have a gain there, which is called open loop gain. We'll understand that later. So A naught is the open loop gain, and then multiply by the difference between your V plus and your V minus. So that's very, very simply what's the relationship between your input and your output. So what is it saying here is this op-amp, if you forget about plus Vs and minus Vs, it's simply taking the difference between these two. It's taking the difference between the V plus and V minus, as you can see here, and then multiplying this difference by a certain factor. And this A naught there can be very large. It can be up to 1 million or 100,000. So you can see here in this way, the op-amp is going to amplify any small difference that you have in V plus and V minus is going to basically cause V out to become plus Vs. Yeah, that's not very useful, but later as we go along, we're going to see how can we use an op-amp in more useful circuits. So let me repeat that. If your A naught there was a very large value, so any small difference you have between V plus and V minus, for example, if we take V plus minus V minus, if we just put some values there, let's say your V plus was 5 volts and your V minus was 4 volts, you immediately get a difference of 1 volt between the two inputs. When you multiply 1 volt by 1 million, you are expecting to get 1 million volts at the output, which is not possible because this is capped by plus Vs. So let's assume that your plus Vs is, let's say, 15 volts, your supply is 15 volts, and your minus Vs is going to be minus 15 volts. It means your output can never go beyond these two. So if ever your output is trying to go to 1 million, it's going to be gamma plus 15. So what are we finding here is, in this simple way of using an op-amp, which we call open loop, later we'll see what open loop means, your op-amp would typically be saturated. What the saturated means is the maximum value you can take is plus 15. So if it's taking a value of plus 15, it means it's positively saturated. If it's taking a value of minus 15, it's negatively saturated. If I try to draw a small graph here of your Vout, so what are we saying here? Basically, your Vout is going to be plus 15 or minus 15 most of the time, because the gain is too large in this mode. So that's what you're trying to say. Okay, so all this is described. Okay, now we've seen the this is the ideal op-amp with a very actually a real op-amp would have a very large gain, but an ideal op-amp, this value here would not be large, infinite. Yep, so this value is going to be infinite for an ideal op-amp. So let's look at some of the properties of an ideal op-amp, and then we're going to build on that to understand how real op-amp is. Okay, so the first property is it has infinite input impedance. What does that mean? You have the two pins there, V plus and V minus. If the this op-amp has an infinite input impedance, it means that the op-amp does not take any current inside, because when your resistance is large, it has impedance is about resistance. When this is very large, the op-amp would not take any power, because when you have very high resistance, it corresponds to zero current. Okay, so it means an ideal op-amp does not consume any power. Yeah, that's an idealistic characteristic. We know op-amps typically would consume power, but an ideal op-amp would take no current inside. Okay, and at the output now, it has no output impedance. That is, it does not cause any loading effect on the circuit it feeds. This is basically saying here, whatever output you feed here, the out, okay, will not be disturbed by the op-amp. It has zero output impedance, so infinite input impedance. Like we said, it doesn't consume any current. And then it has zero loading effect at the output. So this is a very ideal and very desirable characteristic of this type of any device. If you have a circuit like this, means it has no loading effect at the output. So in a way, it will not disturb the output that you are trying to feed. It will not itself consume any have any voltage across it. Next, what I've just mentioned, it has infinite open loop gain. I mentioned the value, for example, 1 million earlier about this gain here, but for an ideal op-amp, this is infinite. This is infinite. This means that any value you have, the slightest difference that you have between V plus and V minus is going to cause the op-amp to be saturated, like we see here. So if your gain there is infinite, this line which you find there is going to be actually totally vertical. If your gain is very large but still not infinite, then you will have a small gradient here. Right? You have a very small gradient, but very steep one, because the gradient of this line basically is going to give you the gain. But if it's infinite for an ideal op-amp, this is not going to be a slope, it's going to be just vertical, because infinite would be the gradient for giving an infinite would be actually vertical. Next one, which we see down the line, is the op-amp has the same response to all frequencies, means it amplifies all frequencies equally. So if you are trying to amplify a signal, let's say 50 hertz or 1 kilohertz or 1 megahertz or 1 gigahertz, an ideal op-amp would have the same characteristic for all frequencies. But as we see later, normally a real op-amp would not behave like this. As you start increasing the frequency, the op-amp will start reducing in gain. Now we're going to see that later. So these are the four properties of an ideal op-amp. Okay, and we look at that equation already. Yep. So this equation is a very useful equation which relates your inputs. So here when you take V plus minus V minus, you get a delta V, so difference between your inputs. And then when you multiply that by your open loop gain, get your output. Okay, so let me repeat that. If your A note here was infinite for an ideal op-amp, any small difference you have between the two inputs would cause output to go to plus Vs or minus Vs. Plus or minus Vs. You're going to saturate positively or negatively. Yeah, we have some graphs coming later to show that. The only situation where your Vout is not plus or minus Vs is when these two are exactly equal. So V plus minus V minus is going to become 0. 0 times A naught would be 0. Yeah. So the only condition when your output is not equal to the plus Vs or minus Vs, if we go up here, like we said, your output can swing between plus Vs and minus Vs. And if your gain is very large, it will be either this plus Vs or minus Vs, depending on which one is larger. Yep. In this case, we've taken 5 minus 4, means you are assuming your V plus to be 5 and your V minus to be 4. So since your V plus is more than your V minus, your output is taking plus 15. But if you assume now that this one is 5 and this one is 4, so you would have 4 minus 5 here, which is minus 1. But you try to multiply minus 1 by a very large value, you tend to get minus 1 million, which you thought. So it's going to saturate at minus 15. Okay, so this is how you can find the polarity of your output. So the only case where your output would not be your supply voltage would be when this difference here is almost 0. Yeah, get a very small difference here, then you then your output may become 0 here. Okay. So what is explained clearly, and this is the graph I've just explained to you. So this is for an ideal op-amp, where the difference there is your delta V, so your V plus minus V minus. If it's equal to 0, then definitely your output is 0. But any slight difference with positive or negative is going to cause saturation positive or negative. So when this line here is exactly vertical, this is an ideal op-amp with an infinite open loop gain. But in practice, if I just show the graph for a real op-amp and then we come to properties, so this is going to be the graph you will typically get for a real op-amp. So the grade of this line here is going to be equal to the value of A node. Okay, so we've said even if A node is not infinite, it's going to be a very large value, typically around 100,000. So imagine the gradient of a line which is 100,000 is very steep. So here is drawn for clarity, but typically this is very, very steep. Yeah, because for a real op-amp, even if it's not infinite open loop, it's a very large value. So let's look at some properties now, comparing our the properties for an ideal op-amp to that of a real op-amp. So remember, for an ideal op-amp, we said it has infinite input impedance, meaning it doesn't take any current in. So a real op-amp would not have infinite input impedance; it will have very high input impedance. That's the difference. So it's going to consume a very little power. It's going to take a little bit of current because the input impedance is not infinite; it is very high. So similarly, for the ideal op-amp, we say it has 0 output impedance, which has no loading effect. But a real op-amp now would have a small output impedance, so it's going to cause some sort of a little bit of loading on the circuit. So it will influence the output to some extent. Okay, and we mentioned about the gain. So for an ideal op-amp, it was infinite, so a node, but for a real op-amp, it's going to be very high, typically around, like we said, 100,000, 1 million. Now, we've talked about the frequency response as well. So frequency response for an ideal op-amp was uniform, means all frequencies is amplified by the same amount. But for a real op-amp, we find that the frequency response is not uniform, but it does amplify all frequencies by the same gain. Typically, as you start increasing the frequency, the gain will start dropping. So if I want to draw a characteristic, we'll look at that later. Typically, this is going to be the performance for an ideal op-amp, where as you're increasing frequency, yeah, so this axis is frequency, your gain is not changing. So this is your gain E. Okay, so this is what you expect. What you expect for this is what you expect for an ideal op-amp. But for real op-amp, as you start increasing the gain, the frequency, the gain will stop dropping like this. As you increase the frequency. Okay. So we'll look at that later. Now, one important difference as well when you compare the ideal and real op-amp. Remember, we said your output typically saturate at plus or minus Vs. So if your supply voltage was plus or minus 15 volts, we are shown for an ideal op-amp that your output can go till plus 15 volts. But in practice, since you have typically transistors and you have drops in your circuit, the output voltage for a real op-amp does not typically go to the supply voltage. It is typically taken to be 1 volt less than the supply voltage. For example, like mentioned in the handout here, if your supply voltage was plus or minus 12 volts, typically the maximum output which can be taken by your output terminal will be plus or minus 11 volts, so 1 volt less, because you do have drops in the circuit. Okay, so I've already explained this graph here, which you would get for a real op-amp. So again, an ideal op-amp is going to be exactly vertical here, because the gain is infinite. But for real op-amp, the gain is large. It means you would have a slope. Okay. So some examples are given here, which you can consider. So, for example, here an op-amp has an open loop gain of 100,000. The output voltage can swing between plus 12 volts and minus 12 volts. draw over gain characteristic showing a threshold for this axis. So if you just take this 12 volts here, you divide by this gain there, because we know from our equation is V naught equals to A naught multiplied by delta V, where delta V is just V plus minus V minus. So basically you're trying to find here for the maximum value of your output voltage, which is 15. So what value of delta V is going to go plus 15. Yeah. If you exceed this delta V, definitely it's going to go flat here, because output cannot go beyond that value. So if you just plug in the gain, which is given to you, 100,000, and if you find the, sorry, I've done this small mistake. This has to be 12. Yeah, this is not 15. This is 12. According to the question, this is 12. Yeah, so if you just replace here, you get a delta V of 120 microvolts. So if your output exceeds 120 microvolts here, you're going to have plus 12. So 120 microvolts is the limit. It's the limit between saturation and then the linear region you have here. So on the negative side, same thing. If you go beyond minus 120 microvolts, you have minus 15 volts here. So in the range here between the two, you have a linear region, and the gradient of this line here is actually 100,000. Okay, so very simple exercise which we done just now. So again, this one is not very useful for us, but this is the characteristic of a real op-amp. So you can read about that. Now, the discussion we just had on an op-amp is a typical case of a comparator. A comparator is a very simple circuit which allows you to compare two signals, like the name is saying. So if you have a signal being applied to V plus and a signal being applied to V minus, if you're comparing these two, the output would tell you which one is larger. So since we said the open loop gain of the op-amp, in this case here, your A naught is very large. So typically, any small difference you have between V plus and V minus is going to cause positive or negative saturation. So if your V plus was larger, it's going to go to plus Vs. If your V minus was larger, it's going to go to minus Vs. So basically, by looking at your output there, which would be typically a square wave, yeah, because it can be either here or here. So it's going to be basically be a square wave. And at the points where your output is plus, so during this region here, your V plus would have been larger, and wherever your output is negative here, negative Vs, your output, your input, it means that your V minus was larger than V plus. Yeah? So this is a simple comparator. You're basically comparing your V plus and your V minus. So if V plus is larger, you have plus Vs. If your V minus is larger, you have minus Vs. Okay. Okay, so let's consider these examples here. Saying assume an ideal diode, an ideal op-amp. Sketch the output waveform for the following input waveforms applied at V plus. So if you look at this circuit, we're going to find that your V minus is grounded. Okay, so your V minus is grounded, and then your V plus is having these signals connected to them. So if you want to analyze how this circuit behaves, this is behaving like a comparator, like we said earlier. You're basically comparing these two. So like we said, if your V plus is greater than V minus, in this case, your V minus is simply grounded. So for all situations where your V plus is more, so when your V plus is greater than your V minus, and your V minus is nothing but equal to 0 volts in this circuit, yes, it's grounded. So whenever your V plus is more than 0 volts, you would have plus Vs. Okay, so what is that region? It is this region here. So it means in that region there, your output is going to be, so if I just draw it here. So in this region here, your V out would simply be plus Vs. And then when it goes on the other side there, so the other situation is when your V plus now becomes less than V minus. So this is where you have negative saturation. Then your V out would be minus Vs. So you're going to get a square wave like this. Okay, so you can see your threshold in this case is actually your V plus, your V minus, which is fixed at 0 volts. So let me just explain this graph now. So in this range here, this positive half cycle here, your V plus is more than 0 volts, so your output will saturate plus Vs. So this is plus Vs here, or the graph shown in right. So this is plus Vs, and the other side is minus Vs. So for the region where your V plus is more than 0 volts, you have positive saturation, and then in this case you find in a negative half cycle where your V plus becomes less than your V minus. That's going to be naturally negative saturated, and then so you have a square waveform. So it's basically comparing the two inputs. And if you want to show here, this is your the level of your device, which is at 0 volts. It's at 0 volts. Okay. Now let's consider this one. So same way, this is going to be the level of your V minus. So whatever you have a positive here is going to be positively saturated, and then when your V minus becomes larger than your V plus, it's going to be negative saturated. Which are basically comparator. Yeah. So what I've drawn here in red, this part there is going to be your output. Okay. Now let's look at this question. What's saying here? A potential divider is used to set the inverting voltage at +2 volts. Okay. Now, what are we saying here? In this case, your inverting voltage was connected at 0. As you can see, it's grounded. This is grounded, so it's at 0 volts. Now, what if we set the voltage reference somewhere else? It doesn't need to be 0 volts. You could connect, for example, this line here to a voltage divider, and then this could be set. This is what this question is saying now. A potential divider circuit is used to set the inverting voltage at +2 volts. Show how this can be achieved and sketch the corresponding output waveform for the sinusoidal wave. So, okay, so I remove everything. Now, what are we saying here? We are setting the reference instead of this being 0 volts. Now we're saying it's setting it at 2 volts. Let's try to draw a straight line here. So it's just set at 2 volts. What's the result? So basically now in this region there, whenever you're below that line there, so this is what I've drawn here is your V minus, which is set now at 2 volts using a voltage divider circuit. How can you do that? Very simply, you could just use a voltage divider with a resistor here. You can just do a voltage divider. So if you have something like this, and then you put this at 5 volts. If you want to get 2 volts here, you can put this one at let's say 2 kilo ohms and this one at 3 kilo ohms. So you have you can put 2K here, so that you don't have large currents. So if you do voltage divider now is 2 or 5 times 5, so you get 2 volts, and then this point there is going to be at 2 volts. This is going to be connected to your op-amp in that way. This is going to be the negative terminal, and the positive terminal will of course be connected to this side. So this is the scenario. We are now not fixing your V minus, this is your V out. We are not fixing your V minus at ground now, and here we are fixing it at +2 volts. So this is what we're showing here, +2 volts. So for all cases where your V plus is higher than the 2 volts, you have positive saturation. So you have a square wave here. You are starting here, you have a square wave. And then for the regions where your V plus is less, so this region here, from here, this whole part there, and all this region which is below the 2 volts line, you will have negative saturation. So your output would be shifted to minus Vs. So you can see as you play with this line there, you move it up and down. You're going to play with the your output. So ultimately, if you raise this line completely, it becomes here. So at the top there, you will not have any value of any output voltage or plus Vs. You have everything at minus Vs. As you shift this line up and down, you are increasing the amount of time the signal is at plus Vs or minus Vs. So this is one method called pulse width modulation. This is used to control speed of motors. So as you move this line up and down, you are increasing or decreasing the amount of time that your signal is high or low. And typically this would accelerate or decelerate your motor. So it's called pulse width modulation. So in short form, abbreviation is pulse width modulation. So this is one method for controlling speed of motors. Okay, now let's look at this one. So the input signal at the non-inverting terminal. So it's the second part now. The input signal at the non-inverting terminal. Non-inverting terminal is +1 here. Is a sawtooth waveform as shown below. So you're applying this signal there at your V plus. This is what you're saying. Okay. Now the reference voltage. The reference voltage applied across the inverting terminal is variable by adjusting a potentiometer. So very similar to what you said earlier. Sketch the output waveform for the following values of Vref. So if, for example, you are setting V reference there, remember your V reference is connected to inverting terminal, Yep, and your sawtooth waveform to non-inverting. So for example, this is 4 volts. You're going to have, this is going to be your V minus. So you can very easily sketch your V out there. And like we discussed, whatever, so this is your V minus shown in red there. So whenever your V plus is higher, so this small region here and this region here, your output would be plus Vs. And for this region here, which is lower, it's going to be minus Vs. So basically, you're going to have not a square waveform, yeah, because it's not actually square. The amount of time the signal is high or low is not the same. But as you move this up and down, as I said earlier, you're changing some amount of time. Let's take a case where this is 1 volt. So now your reference is here. Yep. So you can clearly see if you set your V minus to 1 volt, yeah, you're actually having a large amount of time. So for this region here now, your signal would be at plus Vs, and this region here is going to be at minus Vs. So again, you get a square waveform where you are increasing or decreasing the amount of time the signal is at high. So if it is 5 volts, means you're fixing this on top completely there. So you get a case where you're, so if you shift this line up at 5 volts there, you're having an output waveform which is always fixed at minus Vs. If now the last one you're fixing at minus 3 volts, so if you're somewhere here, so you can see here you have a larger region now where your V plus, your non-inverting input, is going to cause all this region here is going to cause your V out, your plus Vs. Only this small region here is going to cause your output to become minus Vs. Because whenever your V minus is larger than your V plus, it's going to be your output voltage V minus Vs. Okay, so as you can see here, basically this part of the question, what happens when the reference voltage is changed? So basically, as you move this line up and down, you're increasing or decreasing the amount of time that your output voltage is at plus Vs or minus Vs, and this is called a pulse width modulation method, like I've said. Okay, now let me just start that, and then I'm going to continue that in a particular video. So the circuit we've considered till now are called comparator circuits, where your output is typically either positively saturated or negatively saturated. It has some applications like you've seen here, but not very useful. If, for example, you want to amplify a signal, let's say you have a temperature probe or pressure probe, and you want to amplify the signal, it's not very useful that your op-amp is always saturated. Let me just give you a simple example. If, let's say, you're trying to measure temperature, it is now 25 degrees, and suddenly it becomes 30 degrees and then 35 degrees, you would want to have an output which allows you to differentiate between the 25, the 30, the 35. If at all these input temperatures, your output was saturated positively, that means you're not able to differentiate. You're always having one voltage at your output, so it's not a very useful circuit for interfacing with sensors, for example. So let's find now a method which can be used to limit the gain of the system, because that's the problem of this of an op-amp in open loop mode. The gain is very large. When the gain is very large, it's going to cause positive or negative saturation, as we've seen here. So one method to control what is called negative feedback. So what do we do negative feedback? So you can just read on that here. Negative feedback, basically, as you can see here, we take part of the output and we feed it back to the input. So this method is called negative feedback. You have a module in level 4 on control system. So when you're going to study that, you understand better how does negative feedback actually bring about stability. Yep. The circuit we considered earlier in open loop mode, you can liken this to be instability, means your output is only plus Vs or minus Vs. So it's always saturated. It's always completely filled, if you want. So if you want to have an output signal which is not saturated, you want to have a better stability of your output, then you're going to have negative feedback. What is negative feedback? Basically, it's about feeding part of your output to your input. When you do that, then the circuit becomes more stable. Okay, and it will not be saturated plus Vs or minus Vs anymore. Now, like I've said earlier, in this symbol here, you still have these two supply terminals. Be careful, they're still there, but we typically don't show them on all circuits. Okay. Now, let's see how this behaves. Now, for us to have stability, it means this terminal you find there at the inverting terminal should be the same as this terminal. If you have any difference, the negative feedback that you're applying would ensure that these two terminals are the same potential. For the simple reason, if they were not at the same voltage potential, your output will be saturated. So this is called a virtual earth approximation. As you can see there, your plus terminal is grounded. So if these two signals have to be at the same level to go stability, but if this is 0 volts, this one would also need to be at 0 volts. It's called a virtual earth approximation, and it's a very important principle that we apply in analyzing op-amp circuits with negative feedback, because we are putting negative feedback simply to bring the circuit to stability. We don't want the V out to be just plus Vs or minus Vs. For the only condition this can occur is when these two V plus and V minus are almost the same, like you've seen earlier. So if this is grounded, you would assume it's at 0. So you can very easily see now this is just a simple voltage divider. Yep. So if you apply the rules of voltage divider, you can very easily derive the relationship between V out and V in. So V out over V in is simply output over input, so you get a gain. Yep. So if you derive that, it's showing clearly here. You're going to get that expression here. So the gain of this circuit is simply minus RF over Rin. That's what you're going to get. Okay, so I would encourage you to read on that. So it's fully derived in your circuit. This is a version of approximation I mentioned about. And you would want to find the relationship between V out and V in. That's the whole purpose of this analysis. You want to find by what amount your input has been amplified by the circuit. So V out over V in gives you this. So very important here. Now we have introduced a term called closed loop gain. Before we had an anode, which is called open loop, because there was no feedback. So when you don't have any feedback, you talk about open loop gain. Yep. Now, when you're doing this feedback there, the overall gain now, which is V out over V in, is no more called an open loop gain. It's called a closed loop gain. So how you derive that, you have to simplify V out over V in. In this case, it's equal to minus RF over Rin, as you can see here. Yep. So you can see the value which you get. For example, if I set RF at 5K, let's say, and I set your Rin at 1K. So if you replace the value here, you get minus 5K over 1K. You get minus 5. So you're going to get a gain of minus 5. Now you can see clearly your gain is not very large now. It's not like in millions or 100,000. It is a small value now, which you can control by setting values to RF and Rin. So this becomes very useful now. You can use that to control the gain to avoid saturation. Okay, now why this is called an inverting amplifier? You can see the name there is inverting amplifier. It is still using negative feedback, but as you can see from the gain is negative. It means the output, if the input was positive, the output will be negative. So it's going to invert the phase. This is why it's called an inverting amplifier. It is still using negative feedback, but since the input there is applied to your inverting terminal, you have an inverting amplifier. Okay, now you have very similar circuit. So you have some examples given there where you can plug in the values given here and work out the gain and calculate the output. That can be done very easily. So I would encourage you to do that. The second type of amplifier which we want to consider is a non-inverting amplifier, still using negative feedback. You can see here we are feeding part of output to the inverting terminal. That's fine. But in this case, interestingly, you are applying the input voltage to your non-inverting terminal. That is very important. So again, here you're going to apply the virtual approximation. For this circuit to be stable, this V plus and this V minus should be at the same potential. So you can apply the potential divider circuit there to find the potential here, and then you can equate the two. So this is done for you here. You're going to get an expression as follows here: 1 plus RF over R1. So you can see in this case, expression is not negative.